sure. Yeah, I mean, last week, well, not last week though, I guess, because the course schedule was kind of shifted. So I guess like probably 2 weeks ago, you guys talked about acid derivatives, right? And I guess now you're doing those homeworks that are associated with them.
Yeah, we actually learned it just this past week, carboxylic acid derivatives.
Oh, all right, cool. That's good. Well, then it should be fresh on the mind. And I guess the fortunate thing is that there are a lot of reactions, but I think very few of them you haven't seen before. You know, it's like you can't learn to have, I don't know, synthesized esters earlier in the course without having learned to synthesize esters. Like you just, you know, you've already learned how that works. So for the most part, all of the reactions are pretty familiar. And I don't know, there's not that much to say. I know that when I was taking this, and I'll show my screen now, just to draw like the kind of diagram that I always had. I don't know if Dr. Tong has used the same diagram, but I've seen this one a lot, which is if you have like, you have a sort of reactivity series for acid derivatives. And so up at the top, the most reactive thing is going to be green. Let's use
acid chloride, right?
Yeah, it's going to be acid chlorides. And like functionally equivalent are anhydrides, but they're a little bit less reactive than acid chlorides. Okay, let's see if I can actually give myself some more space. Oh. Nice. Oops.
I can see this would be a good place to rank stuff. This might be a ranking type question as far as looking at reactivity.
Yeah, it could be. Yeah, Dr. Tong might not have gotten all of his ranking questions out of his system yet, so I could see that too. Yeah, it could, right? Especially if you say something like rank, you know, each of these in terms of their reactivity with like an organocuprate or a Grignard reagent or something like that. Or just in general for nucleophilic carbonyl substitution. Something like that. Yeah. And so there's like this series where you can go down to anhydrides and kind of go from there. Yeah, normally when this series is drawn, it doesn't actually show all of the reagents for these things, but I mean, we might as well fill in the arrows here because these are actual like syntheses that you can do. So let's say that you did want to go from an acid chloride to an anhydride. What should you add?
You could just do a carboxylic acid.
Yeah. Yep. Just add some acid. And that's pretty much all you have to do. You just do like a one-step synthesis, which is pretty nice. It's like, I don't know if it's that common that you have to go from like acid chloride to anhydride because again, functionally they do like the same thing, but you know, it's useful to have. Okay, and then typically the way this is drawn is that afterwards we have esters. Right, so here we get esters. Okay, and then what do we add to anhydrides, or you can also add to acid chlorides to get esters?
You could hydrolyze
with just water.
Acid.
Okay, well, so you're saying we should do acidic hydrolysis.
Oh, I'm sorry. That's going to give you,
Just water,
Yeah.
right?
that's going to
Well,
give you carboxylic acids, right?
yeah.
Oh, yeah.
Yeah, okay. So, well, we can go way down here, right? And if we just added water, then we can get an acid. Right? But if we want to make an ester, then
We use a salt, like OCH, like NaOCH3.
yeah, that's an option. Oh wait, whoops. Yes, yeah. So we could do something like that. This might actually be a little bit overkill. These anhydrides and acid chlorides, I mean, they're really reactive, right? And they reacted with water immediately. But we can think of water as being like, we can think of water as being like an alcohol.
Mm-hmm.
So we can have like this, right? And so if we didn't want to replace it with water, but rather make it an ester, we could just have an alcohol as our.
Oh, okay.
Yeah. So we don't have to go this crazy. We could just add like methanol would be fine.
Mm-hmm.
Although this is like if you really want to be sure, you could use that too. Yeah. As you're at this point probably starting to learn, I think you've started chapter 22. If you give it something like a really strong base, right? Anytime you have something like this in a really strong base, this hydrogen is going to be acidic. And so this really strong base might come in here and pluck off this hydrogen.
So it's going to react further. It might take you beyond just the ester.
It could, yeah. Although reacting this anhydride first is like way more favorable. So pretty much all of this would react, and then you would wind up doing it. Then you would wind up pulling off hydrogens. So anyway, this is fine. I'm just pointing out that like now that you're in chapter 22, there's a lot more stuff that you can do when there's bases around, and there's like that's something to pay attention to.
Mm-hmm.
Yeah. Okay. From there, we can make amides. Right, and going up from anhydrides or acid chlorides, going down to amides, or going from an ester to an amide, both are kind of the same situation, right? Like, all that we want to do at the end of the day is just put in an amine, and then it's just going to attach itself on there because amines are good nucleophiles. So, well, anything that has like a hydrogen on there as an amine will be good for this because you need to take something off the amine to be able to do it, right? So, and if you specifically want to go from an ester to an amide, you're probably going to want some heat because this is like not the greatest reaction. Like these are pretty close to each other in reactivity. It's actually possible to even go up this way, I think, but it's like, it's a hard reaction to do. So I don't do it that much.
Is that just because esters are much less reactive than acid chlorides and anhydrides?
Yeah, so it's like this amide is already like pretty happy. It's pretty stable. You gotta like put it through some harsher conditions or put a ton of alcohol in there to be able to go back up to this ester. Yeah, all of the steps in this reaction are actually in equilibrium. There's no step in here that's like totally one directional. So if you really make the conditions favorable, you can go back up this way, but that involves putting like a ton of amide in there, or a ton of alcohol in there, so you can cleave your amide.
Gotcha.
It takes some work, for sure. Yeah, and then over here, you don't have to do all that much work because you have an acid chloride and an anhydride, which are already like super reactive.
Got it.
I think in both of these cases, you need some mild base. Like pyrimidine would work nicely. This is like a nice base because, you know, during the mechanism at some point you're going to, no, I don't, maybe you don't actually, right? I was trying to think about the mechanism and like, what you might have is like an O- here, OR, something like this. I guess you want it under either acidic or basic conditions so that this doesn't happen, because you don't want this minus or plus. So it could be either acidic or basic, I guess. Probably acidic. So that way you protonate here. That way you've protonated here, and then you could pull off like this. Right, and then, yeah, and then you have NR2, right? And from there you just reform you've protonated here at some point, right? Something like that. So this should probably be under acidic conditions. Something like that. Actually, it makes sense that it should be under acidic conditions too, because the mechanism is pretty much exactly the same as the Fischer esterification, right? So that one uses acidic conditions. Makes sense that this one should too. Cool. Yeah, and then if we want to go to an acid, I guess what should we put in there?
Could you use base?
Yeah, so you could use either, so I think you could use base and like a ton of heat. Maybe not a ton of heat, it might not take that much heat. But you could use base, or you could use acid as well.
I guess acid's better because you don't need to do a workup afterwards.
That's true too, yeah. Yeah. So either one of these will work. Cool. This is our whole chart.
Sorry, if you threw H3O plus and heat at any one of these, would it make a carboxylic acid?
Yes.
Oh, okay.
Yeah, you should. Yeah. And well, let's say we want to go all the way back up. And we want to go from an acid to an acid chloride. What should we use?
Oh, SOCl2?
Yeah, exactly. Nice and easy. Yeah. So it's really nice because you can climb all the way back up this ladder and then kind of descend your way down to whichever thing you want to make. And it's not that hard to do this step, at least not on paper. So yeah, there's actually one thing that commonly gets excluded from this list, which I also haven't written here, and it fits in here, which is thioesters. Okay. Let me put these things in boxes so we can tell where they are. Okay. And I mean, making a thioester is like no different from making any of the rest of these, right? You could just give it like RSH would be fine. You don't have to give it RS minus because, I mean, even this group on its own is already like a pretty great nucleophile, so there's no need.
And getting from the thioester to the ester would be the same thing, NaOCH3.
Yeah, yeah. So you could do that, or just the alcohol, either one. Oops. Yeah, either one would be fine. So, yeah. Yeah, unfortunately, thioesters always get left off. But they're here. They're around. Yeah. I think there's some like good number of other reactions that's covered in this chapter too. Like, maybe most of them are just specific cases of these reactions. Like, for example, I know there's like a section on like transesterification or something, or like saponification, but those are just these reactions, or like some variant of the Fischer esterification or something along those lines. I personally never found it that helpful during this sort of section, or this chapter of the course, to like remember each of the mechanisms as if they were their own thing, because they're kind of all the same mechanism. You're just using a different nucleophile to attack onto the carbonyl, but otherwise it was all they're mostly the same mechanism. So that's good, because that means there's fewer things for you to learn. So that's quite nice. I guess we should do some problems now, just because, I mean, yeah, there's not too much more to say about each of the individual reactions, because you've just seen most of them so many. It's good to review each of those reactions, like going all the way back to probably amines and reviewing from there, because that's kind of the point at which you started working pretty heavily with things that, I don't know, carbonyls and things that might be considered carboxylic acid derivatives. So let me pull a problem up. I know you guys said you were disappointed by the lack of synthesis problems on the quiz, so here we go. So here's a synthesis problem. It can be done in 3 steps, and it should be done in 3 steps. Well,
all right. Well, if we're
guys.
If we're starting with an amine, could we throw some protons at it and make it an OH group? Or, ooh, no. We would first want to make this a carboxylic acid on here. I forget how we do that.
Yeah.
Well, I guess
we could think about the ways we know how to make carboxylic acids on aromatic rings, right?
I mean, so I have a suggestion, but it's not going to be 3 steps. I think the mechanism, you could use NaCN and then you could use H3O plus, but that's going to take 2 steps of our 3.
Yeah. Well, so okay, so you want to make a nitrile here, right? And then acid hydrolyze.
Mhm.
Yeah. Okay, and then from there, how would you get to your product?
Um,
Oh yeah, go ahead, Paul. Sorry.
yeah, we do what you said before. You could just use the alcohol.
Yeah. This is
Just
just,
use Fisher.
yeah, exactly. This is just normal Fischer esterification. Okay, well, this is only 2 steps. So if we can go from here to here in 1 step, we're good.
And that is
You can't use NaCN for that.
Not immediately. Not right away. But it is possible to put a nitrile on.
You could do the diazonium salt, but that would be, I mean, you could write it in 1 step, but it's not like in reality 1 step.
Yeah.
let's throw air at it. Doesn't O2 make it a nitrile?
Because we're adding this carbon here.
Oh, we're adding a carbon.
Yeah. Yeah. Actually, so Sarah had the right idea, which is that you could make a diazonium salt out of this, and then from there, it's like you just throw the right thing on there and it'll put a nitrile on. Yes, you actually have to write this as 2 separate steps. It's like sodium nitrite, and then we use HCl, right? And then from there, do you guys remember what compound you put on, or you add to put a nitrile on?
It's the copper cyanide, whatever it is.
Yeah, exactly. Yeah, that's it. So yes, this is written as 2 steps. I think we'll count it. That's like reasonable. Especially because they're 2 steps that come one out like right after another.
Right.
I think in practice, if you were doing this, like, you know, like you write it out as step 1 and step 2, and in practice, I think you would actually just add this, and then immediately after you would just add this and the same reaction. So like, it's kind of 1 step, I guess.
Is there a better way to do this then?
I don't think there's a better way. This is 3 steps, so this is the desired length. So this is good. There is another way, although I think this is pretty reasonable. Actually, the other way involves more like, you know, allegedly 1-step reactions. So, yeah. So I was also thinking how to get this carboxylic acid on there. Well, if we had something with like a carbon, and then we gave it,
Just give it a strong oxidizer, right? And then it'll just put the carboxylic acid right on there.
yeah. So if you do this, then you wind up with the carboxylic acid.
We need to make an alkyl first.
Yeah, well, but you can't do, but like getting to this will take more than 1 step for sure, right? Because from here you just do Fischer esterification. That one's given. You can't get away without that.
I mean, you could react it with an ester, right? You can react the original compound with an ester, which would give you your carboxylic acid, but it's going to be too many carbons, right?
Yeah.
Could we just add a substituent onto our benzene ring and then just get rid of the amine?
You can, so if you wanted to do that though, you'd have to do, so if you wanted to do like Friedel Crafts, or I guess in this case, you'd probably want to do like Gatterman Coke, which involves like formaldehyde, right? What else? CO, HCl, copper something, chloride, maybe.
Seems right.
All
Is
right.
deamination then one step?
Well, yeah, that would have to be a separate step. And the issue is even then, this reaction is going to fail because of this amine.
It's more
Oh.
deactivated than a halogen.
We're gonna have to do a separate step. We're gonna have to put like, we're gonna have to acylate the amine and then put the thing on the ring, and then
Yeah, and
deacylate,
then you have to
take the amine off.
deacylate the amine, get rid of the amine anyway. Probably again using a Sandmeyer reaction. So it's that won't work. So this is too many steps. So here, this will have to go, we'll have to acylate, right? So we'll have to acylate, and then from there, do like Gatterman Coke, and then deacylate. Right, and so on, but this is too many steps as well. Okay. There's another way to put carboxylic acids on the compound, which, let's see, our starting compound was just aniline. It's hard to forget, it's hard to remember. So if we had some way of making this into like a, some kind of halogen, then we could use a Grignard reagent and get this one carbon carboxylic acid on there fairly easily. So, you know, from here we'd be able to add like
CO2.
Yeah, exactly.
Is that one step? Making your Grignard, then reacting with CO2, then acid workup?
Yeah, that's pretty reasonable to call one step.
Okay.
Yeah.
How do we make the BR or the whatever?
That's also a Sandmeyer reaction.
It's also Sandmeyer?
Yeah.
Sandmeyer lets you do everything.
Everything.
Yeah, they're a fantastic set of reactions. Yeah, it's why that's like that set of reactions is one of the ones that I call, that I say breaks organic chemistry, because like you can kind of just do whatever you want with it on aromatic rings. You can't really, there's a lot of stuff that you can't do, and you still need like Friedel Crafts or whatever. But having an amine on an aromatic ring is definitely common enough that like it's super useful. So we do the same thing. So NaNO2, right? And then yeah, you want like HCl also. And we want to make this into like, let's say a bromine. So what do we add?
Copper bromide.
Yeah, exactly. CBr.
Is the cation copper a lot of the time? I know we just did
Yes.
those, so I can't believe I forgot them already, but okay.
Yeah,
Copper.
it's I'm pretty sure it specifically has to be copper.
Okay.
Yeah, you can use, I think, CuCl, CuI, CuCN, CuBr, of course. These are all good. Maybe this one I'm a little bit, I'm not sure about. I can't remember exactly.
I'm looking at my notes right now, and the copper chloride is definitely there. I have potassium iodide instead of copper, but same.
That's right. Yeah, I knew one of these was
Yeah.
different. I thought it was chlorine. Yeah,
Do you need
potassium
heat
iodide.
for that one too?
This one?
There's something you need heat for, yeah.
Chlorine.
Chlorine, okay.
Chlorine needs
Fluorine,
heat?
fluorine.
Okay.
No, fluorine. So you have the
Yeah, that one is
The HBF4, right?
HBF3, and then you have to have heat to add the fluorine to the aromatic ring.
yes. Okay. And this is the only way to add fluorines to aromatic rings, I think. So this one's kind of useful. And if you ever see a fluorine on a ring, well, you probably know like this has to be it. There's also another, which is phosphoric acid, which will just replace it with hydrogen. Here you're replacing with a fluorine. Here you're replacing with these guys. There's a way to do an alcohol, right? Is it just water?
Yeah, I just have like H3O plus and heat. Yeah. So just
yeah.
dilute acid and
yeah, that makes sense. I don't think there are others. Are there? This seems like the full list.
It's just the other one I have is the coupling with, making that like double nitrogen bond. I forgot the like full name of that.
Oh yeah, diazonium, right? Or no?
Oh. Okay, yeah. That's in this first step here. That's what this makes though. Yeah.
No, but I think, Sarah, unless I'm misunderstanding, it's when you like couple two of those together.
Two aromatic rings, yeah.
Oh, yeah. Yeah, I guess if you add another one, then
yeah, exactly.
Yeah, then you wind up with yeah, I misunderstood.
Yeah, that's a pretty great reaction. You're right, I should definitely keep that going.
Yeah, these are pretty good. Something that I've like seen in the past on probably one of my old exams that I remember tripping me up was like a really weird but like I guess pretty powerful synthesis route might be to like stick one of these on and then I guess do something like we just did with the nitrile and then we hydrolyzed it. But you can imagine also doing something like sticking on a halogen and then doing like nucleophilic aromatic substitution. That's like a possibility. That's a weird and I guess kind of uncommon synthesis route, but it could work and it could be really fast sometimes, depending on what you want to put on.
Wouldn't you be better off making the Grignard? Oh, sorry.
No, go ahead. That's fine.
It depends what. I think like, let's see. I mean, if you wanted to make, for example, I'm trying to think of an example. If you wanted to go from like here to make an ether, a really fast way might be like first step, do the semi-reaction and put a halogen on there. So we get a halogen, and then from there,
NaOCH3 CH2 or CH2 CH3.
Yeah, you could put this in there, which is a really strong base.
Okay.
And then heat it, and this goes through the Benzyne mechanism, which I think is a load of garbage, but it's just a ridiculous reaction, right? They spend all this time telling you like, oh, you can't have triple bonds and rings. Triple bonds are straight, all this stuff, or whatever.
Total crap.
Yeah, they're ridiculous. Yeah, I actually, when I was taking the course, or maybe last year or something, I looked this up because I was like, there's no way this is real. Like, it's got to be something else. Apparently it's real. Benzyne has been like experimentally detected. It's like Yeah, no, it's definitely real. It's just dumb, you know?
Yeah, it must do something crazy like when it happens and the like ring sort of distorts itself or somehow to like accommodate that triple bond is the only way I can like conceptually accept that.
Yeah. I mean, I guess there are other situations where we have double bonds and it's kind of like uncomfortable, right?
That's
Like,
fair.
I mean, this thing exists, right?
Right.
This
Yeah.
abomination to God exists. So, yeah,
Oh my gosh, so much energy stored in there.
yeah, I know. Yeah. Um, so, you know, if this is possible, anything is, I guess.
True.
Yeah. Cool. Let's pull up another synthesis problem. There's some more. This one's more involved. It has 4 steps now. So that's fun. Let's see where to go. Oh, it's way up here. Okay. This all the way down. Cool. Okay. There's a good amount to this one. So any thoughts to start off?
I forget, is carboxylic acid a meta director?
Yeah.
Okay, so then I guess first replacing the bromine with our carboxylic acid, which couldn't we?
Mg.
Yeah, just
Yeah.
right here.
Mhm. Yeah. I thought the same thing.
Plus.
Right. And so let's just do that. Okay. So we have this.
Then can we put on an NH2?
Okay, sure. That'll take 2 steps, right? We have to do,
HNO3, H2SO4.
yeah. So we have to do this first. Right, and this is meta, so we'll go there. Let's see, what catalyst do we use? Let's pick the simplest one because
Oh, okay. Yeah.
I can never remember any of the other ones, but this one's useful for the Clemenson reduction, so we might as well just use this one.
That's not going to touch our carboxylic acid, right?
No, I don't think so. I think it only works on aldehydes or ketones, but the acid is too oxidized for either of those. For this to work on. I think so. Yeah. If we wanted to be safe, we could use iron and HCl. I think that's weak enough conditions that it won't work here.
So are we good? Can we just do the NaNO2 HCl thing plus Ki? That gets us there.
Yep. Yeah, I'm with you. 2. Yeah, potassium iodide, that's the one, right? So Ki. Yeah, that's it. That's this is 4 steps, so that's all we needed. Yeah, there's like no more to say than that. You could have also gone backwards, right? You see that this is a meta director, right? So you had to have put this iodine on there second. But how do you know how to put iodines on aromatic rings? There's only one way. So that'll work you back to this step, and from there, it's, you know, you only have to think about 1 step backwards. So yeah, doing it retrosynthetically would also work. It would get you.
Can you do half I too? Or just throwing I2 at it, at a benzene ring? Is that it?
I don't think so.
Okay.
I don't think iodine's reactive enough. Iodine's like, I think it's like the least reactive of the halogens, really. And in general, right? Like, I mean, we know that like if we put just this in like an aromatic ring, but you need an acid catalyst to be able to do anything right like this. So this needs like FeBr3 or aluminum trichloride or whatever, right? And so then if you give it, and if you had a deactivating group, this is going to need even more work to get something on there, right? And we're also using iodine, which is weaker than bromine. Plus, this is a deactivating group. Yeah. And I guess, I don't know, I haven't seen if it's possible to just do like something like this. I don't think it is, because if that was the case, then this would be a much easier problem. And iodine is generally pretty weird. It doesn't like to react the same way as everything else. So maybe if you've seen this though, then that would just make this a two-step synthesis. But I don't think that this proceeds. Yeah.
Do you have any more for us?
What, for this problem, or just?
Oh no, more problems.
Oh yeah, they're coming. Let me put this away. Let me save this file. I don't know if you guys are able to see whenever I'm saving files or not.
We did get a reaction very early on in our aromatic reactions that was using I2 and HNO3.
And it put iodine on there?
Yeah.
All right. Well, that's a two-step synthesis, so.
But I'm not, yeah, because it was right. We like looked at the bromination of benzene, the chlorination of benzene. And after that, we looked on putting an iodine on there.
Yeah. Well, I guess in that case, then it's possible to do it in two steps. That would work then. I can't see the carboxylic acid interfering in that at all. So yeah. Well, neat. I guess that would work too.
Nice.
Here, let me put the next thing now. Oh, this question's pretty quick. So copy. Here we go. Yeah. Yeah, so the questions that we give this anhydride to this acid. And okay, so we form this anhydride, right? That's, I guess, not too incredible. But then we give this out, we introduce this alcohol to cleave this, and we only get one ester. And so I guess the question is, what ester is that, and why do we only get that one?
Oh, that's, yeah, the anhydride on, we just did this, but I already forgot it. The anhydride on the right will be more reactive because it's attached to the fluorine. It has a carbon attached to fluorine, which is electron.
You're talking about the inductive effect?
Yeah, electronegative. So it's going to be more delta positive.
Yeah. Yes.
And less steric, actually. probably more steric hindrance, but like not a big difference.
Yeah. Yeah, I guess let's think about this one. Here we go, right? So here we have electrons being stolen this way. And yeah, I guess electrons also being stolen this way too. Which should make this carbon more positive. Yeah, so I would agree.
So the inductive effect makes the carbonyl carbon more electrophilic.
Yeah. Yeah, I think it should. Yeah, I would expect this. That kind of makes sense. Yeah. So I'm looking at the solution simultaneously. It actually says the other way around. So I guess let's think about that one.
Maybe the dipoles cancel each other. The net dipole is less because they're dipoles going in somewhat different directions. I wouldn't think intuitively that would be it. But
no, it shouldn't be that way.
The only thing I can think is just steric hindrance then. You know,
the H's aren't that much smaller than the F's, right?
No,
Yeah.
they're pretty similar in size. Yeah, the solution says that it's because this at the end of the day is the better acid, and so it's kind of going to be better off as being the acid. That doesn't make a lot of sense to me though.
Yeah, that kills me. I wouldn't have gotten there.
No, I don't.
But why would you want a stronger
so-
acid?
No, so it actually says it doesn't say stronger acid. I misread. Is that because this is a better leaving group?
Oh, because of resonance or electron donation from the F's. That's what I meant.
So, yeah, well, yeah, because this is the much weaker conjugate base, I guess. Like this. This is happier, just floating around than this is. Right. So if we go through this sort of mechanism, right, we go here and then, right, we give it our alcohol. Then we kick up here and we kick down here, and this is better off leaving.
It's funny in lecture, I think we went over it with specific emphasis on electron withdrawing groups and electrophilicity of the carbonyl.
So actually,
that's hard for me to reconcile.
Yeah. Actually, so I think this problem might be better framed in terms of a different discussion, which is if we have these two, and let's say we react under really cold conditions or under really hot conditions, I think we would get a different answer for each. I would expect. Because this here is the thermodynamically favored, because the products at the end of the day are more stable. And I would expect that this is kinetically favored.
So the one that's kinetically favored is the more reactive one. I mean, that's the that will be, that carbonyl is going to be the one that's more reactive, basically.
Yeah, I think so. So at low temperature, we would get kinetic, and at high temperature, we get thermodynamic. Yeah, I would think so. Maybe we are wrong that this maybe we're wrong that this carbonyl is actually more reactive at all. I don't think that's the case though, right? Like this is definitely electron withdrawing, right? It definitely likes to pull electrons towards it, as does this. And we have like, I mean, it's not like the dipoles cancel out, right? Because we have, for example, carbon dioxide, which we do reactions on. So, you know, like here the dipoles or the bonds also pull electron density away. So I would think this carbon is more reactive. Yeah, I think so. And so in that case, it probably comes down to, it can come down to which conditions you're doing under, I guess. Yeah. I mean, maybe you would also have to do, you'd have to like look at the different energies, right? Like, is it the case that it'll depend on which step is kind of the one that's limiting, right? Like if you have, for example, this, just let me draw the intermediate, right? So if like this is your intermediate, right? And the limiting step is this. Is just like detaching the other, like taking the leaving group off. If this is the limiting step, then you would wind up favoring the one that we didn't get, right? You would favor this, right? Because if this is limiting, then this thing is just going to pop back off, and it's just going to go over this way to the other carbon, right? Because if it can't pull this thing off, then it's just going to go elsewhere. If the limiting step is attaching onto the carbon, though, then we'd get the other solution. So it's kind of, I don't know, it's hard to say. This is something that we can't really infer just based on looking at the problem, I think.
The only other thing that I can think of is, I remember it might have been in like the text or something I was looking at online, when that alcohol does the nucleophilic attack and like pushes the electrons up onto that oxygen, one of the carbonyls, and then they're both attached to that oxygen, or the carbonyl carbon, I guess. So then you have to think of like which one would be a better leaving group, and the one with the fluorine would be a better leaving group, like a weaker base and a stronger conjugate acid. Maybe that's what the problem solution is saying. So that's going to get kicked off, whereas the alcohol will stick around. But then there's still that question of like which carbon itself would be more reactive.
Yeah. Yeah, it's pretty complicated. And then, it's not like, I mean, this is not like an amazing leaving group compared to the other one, right? They're both stabilized by resonance. Like, if you look at the pKs of them, they're off by like 1 or something. It's pretty small. So
right.
Yeah, I don't know about this one. It can kind of go either way.
Interesting.
In my mind. Yeah. So yeah, I guess it could go either way. We'll maybe, if it's fine with you guys, we'll shelf this problem and
Yeah.
do some more syntheses because that's more fun. So let's get a synthesis problem instead. Because that's just better. Here we go.
I say we start by throwing an HNO3 on that phenol.
Yeah, I would agree. So do you want to put a nitrate on there and then reduce it?
Yeah, nitrate, then reduce it. Then we'll have an amine that we could throw a carboxylic acid at, right? Or no,
Is the game plan?
Chloride.
acid chloride, yes.
Sure.
Is the game plan then to remove the alcohol later and add an alcohol at a different position?
Well, isn't
You just flip it.
yeah, isn't this it's called
Oh, it's pair directing.
phenols are pair directors. Yeah.
Oh, okay.
Yeah.
Yeah. Sorry, you're good. My bad.
Yeah. Oh yeah. Okay. Cool. While you guys have been saying that, I've been also stuck trying to remember what this is. Yeah. There we go. Nitric acid and sulfuric acid, right?
And do the same thing with the ZnHG HCl deal.
That's right. We picked the easiest thing. So.
And then, as Sarah was saying, we could just smack an acid chloride at it.
Yeah. Yeah, acid chlorides are fine. In this case, I might go with the anhydride. Not that it would make a difference, and I think either way it would be fine. But the anhydride is slightly less reactive, so it might be a bit more selective.
Mm-hmm.
So it'll tend to pick this guy because it's a better nucleophile.
That makes sense.
That's like a minor distinction, I think, though.
Oh, because if we use acid chloride, is it possible that would make an ester with that phenol group?
Yeah.
Yeah, I was about to say.
To be
So
extra,
this is like,
sorry. I was gonna say, to be like extra careful, could we like throw some TIPS chloride at it and like just like to protect that alcohol just in case? Because isn't it possible that it might react with? I guess it wouldn't react with the anhydride.
What's the reagent to remove TIPS again?
It's TIPS. Wait, I gotcha. It's TIPS TBAF.
TBAF. TBAF wouldn't mess with the other group, would it?
I don't think so. Right?
Okay.
I'm pretty sure it only is like extremely selective for alcohols and like whatever TIPS. I think TIPS chloride only interacts with alcohols and TBAF only interacts with TIPS chloride. So.
Okay, sweet.
yeah. Yeah, I think so. I think TIPS CL only reacts with alcohols. It probably doesn't react with amines. That's a kind of interesting question because like amines are better nucleophiles, so I can't see why it wouldn't, but I've never seen that happen. So I'm not sure. Fortunately, you don't need to because this amine is just a way better nucleophile, so it'll react way better. But yeah, that's an interesting question though, because I don't know if TIPCL will react with the amine or not.
Because my one worry is even if we use an anhydride, wouldn't that anhydride, if there was enough of it, wouldn't that create an ester with the alcohol group? So would it, assuming that TIPS chloride doesn't interact with amines, would it be like a safe bet after we do our like ZnHG just to protect the alcohol group?
Yeah, it'd be reasonable. Yeah, either way, you're going to get some waste product. It's somewhat just inevitable. But Yeah, protecting with TIPCl sounds fair and fine.
Sorry, stupid question. Would TIPS react with carboxylic acid? Like
I
the
don't think so.
OH? Okay.
I don't think it would. Carboxylic acids are pretty bad nucleophiles at the end of the day. So I wouldn't expect it to. Cool. So that one wasn't crazy. Let's do another. Look, here it is. Oops. Amines. It's everyone's favorite. By that I mean, when I took this course, I thought amines was like the hardest chapter, so maybe not your favorite.
So that's just an acid chloride to, ooh, but we have to do, so what would be the best thing to do here first? Because we want to add on another carbon, right? 3, 4, yeah.
Could we have, oh wait, never mind. We can't do it in so few steps.
I think you can do this in 2, maybe 3 steps. 3, it depends on how you count them, but I think there's actually a way to do it in 2.
Because I'm just confused about how we want to get this.
Could we just straight up react the acid chloride with the amine? Oh, never mind. Sorry, because then you're going to be left.
Ooh,
Could
there's
you?
an interesting. Go ahead.
Yeah, I think you might be able to do that because then you're gonna.
So, yeah. There's an interesting way to do it with this, I think. I don't know if it would work actually, but it's interesting to think about. So if we reacted with the amine, we would get, let's see, what amine do we need? NH2 methyl, right? And then usually when doing these things, we want some base to pick up one of those hydrogens, right? And so, well, there we go. There's nothing there. Oops. So now we have the amide.
Yeah, I mean, if you try to remove the ketone, reduce the ketone, and then brominate, you're going to end up brominating at the allylic, not next to the NH, right?
Yeah.
Okay.
Yeah. So I'm actually looking up the reaction that I was thinking of doing, but I don't think it would work.
Is there a way to reduce away an alcohol? Because couldn't we convert that ketone to, like, using a Grignard reagent? We could make it an OH with another methyl on it. So if we did like MgBr-CH3, that would be the alcohol and a methyl group there, right?
So I think if you use the Grignard reagent on this amine would come off.
Oh, okay.
Yeah, it probably would, or it would just get kind of messy.
Oh, okay.
Um, let's see. Yeah, I'm looking up what I was thinking for this route of synthesis, but I don't think you can do it. No. No, you can't, which is very unfortunate. So my thought was, because from here, all you need is to get a methyl on this carbon. That's like the entire goal. So my thought was, okay, well, how do we know how to replace carbonyls with carbons? Use the Wittig reaction, right? And so you could use PPH3, CH2, right? And then this was my thought. It turns out you can't actually do this. Oops, and that's just a regular carbon. And then you would reduce. But as it turns out, this doesn't actually work. You can only do the Wittig reaction on like ketones or like proper aldehydes, like aldehydes are like proper ketones, not like amides or esters or anything. So unfortunately, this doesn't work.
Could you just do an organolithium, like just like lithium methyl, because that'll do a nucleophilic attack at the carbonyl carbon, right?
But wouldn't that also remove the amine? Oh, are you saying do that first?
I don't know. I guess that's a good question that it might remove the amine.
Yeah. So if we do an organolithium, then some of the time it'll wind up adding twice. Even if we add just one equivalent of
Right.
organolithium, it still might add twice sometimes.
Mm-hmm.
But that is a very good thought.
Could we react with that carboxylic acid in the first step? That also has like the amine on it. So it's a carboxylic acid.
So like react with an amide? Like
Yeah.
Like an amide on one side and what would be?
Okay. So if we had an amide here and then we did something like this. Well, okay, it doesn't need to be, it could be like this. So I drew an extra carbon, but it doesn't need to be, right? So it could be something like this, and then we can do that. But the question still is, how do we get a methyl there?
Right.
Yeah. Doesn't help us.
At the end of the day. Yeah.
If we bromine it, it's not going to, I mean, if we reduce, if we do like any BH4 to get rid of our or I guess LiAlH4 works to get rid of our ketones, or our ketone and our aldehyde. And then you try to brominate, the bromine's not going to go onto the position right next to the amine that we want it to be, right?
So if we did something like this, yeah, I'm trying to keep up with you, and then we brominated. We would get
Allylic, right? And that's not going to let us put our methyl where we want it to go.
Still won't work. So I like this way, adding methyl lithium.
Could we do the methyl lithium after we add our amine, or would that cause that cause it to be the amine to be a leaving group?
So it would. Adding any amine to this acid chloride is going to instantly turn it into an amide, right?
Okay.
But well, that's not great because then that amide is going to leave if we try to use any organometallic to add a carbon on.
Mm-hmm.
Yeah. So we can't use organolithiums. We can't use Grignard reagents. Is there a different thing that we could use to add that methyl on?
Organocooperate.
That's right. Organocooperates. Yeah. An organocooperate would be really useful here. So let me just redraw the whole thing.
If we go through the difference between organocooperate and Grignard and which reactions we use those for?
Yes. Yeah. So so organolithiums or Grignards, for almost every case imaginable, they're exactly the same. I remember you guys mentioned there was last week or 2 weeks ago or something, there's one case where organolithiums are different, which is, I think, when you were trying to like make an alcohol out of an acid, like a tertiary alcohol out of an acid. I think in that case you needed to use specifically organolithiums, but otherwise in all cases Grignards and organolithiums are the same. So
It was carboxylic acid to ketone, I think. Can't use Grignards.
Yeah. That makes sense. So in general, these are all the same. So if we have, well, these two are the same. So if we have like an acid chloride or an anhydride in either one, and we add like, I'm going to use for all of these methyl lithium. Well, maybe I'll use R just to be very clear about which one is. So RLI or RMGBR. So these will add, and they'll actually add twice in both cases. In either case. Let's see, what's next most reactive was aldehydes. And these will both react. Okay. Then we had ketones. Again, both react. These are going to react with everything. If we have an ester, it's actually going to take that ester off. The ester will come off as a leaving group and will add twice. Okay. I think amides, at this point you're pushing it, but amides can probably also add twice. And then lastly, like you guys were saying, for acids, this one is organolithiums only, but if you add two equivalents, it'll make a ketone, which is because it goes, after aqueous workup, which is just because it goes, it can only add once, since alcohols, the OH minuses are terrible leaving groups. So, or the O minuses are just awful leaving groups. So it'll add once. And then once you do an aqueous workup, you have two alcohols on the same carbon. You have an acetal, or I don't know if that's considered an acetal or not, but you have two alcohols on the same carbon, which are gonna, one of them is gonna kick the other one off, so you'll get this ketone left. Okay, so that's that. Cuprates at doing all these reactions really suck. So if you give it an acid chloride or an anhydride, let's just do CuLiR2, sure. They're only going to add once, which is really nice. So you will just get the ketone. And then all of these reactions, cuprates can't do it. Okay, so cuprates can just do this. That's all they're good enough to do. There's some other nice stuff about cuprates, some other reasons that like we actually use them and think that they're good. So if you have like, if you have a substituted epoxide, this is going to make a mess. Okay, but cuprates will react selectively. So they are going to react on whatever side is less substituted, I believe. Yes. Yeah, they react on whatever side is less substituted. So cuprates can do this. If you have a Grignard reagent or an organolithium with anything with like a halogen on there, right, which includes like these two things, but this also goes just in general for other things that have halogens. This will do metal halogen exchange, and I can never remember which part gets exchanged, but this does, I think, at the end of the day, the like lithium goes onto here, and then you get like something like this. Although I can't remember exactly. I know it definitely does metal halogen exchange, but it's always hard for me to remember which way it goes. Have you seen metal halogen exchange? Has Dr. Tong mentioned it or talked about it?
I don't think so.
Yeah, I don't.
Okay.
It doesn't sound familiar to me.
All right, you might not need to worry about that one then, which is good for you. On the other hand, cuprates can actually, I think cuprates will couple here. So cuprates will couple, which is what you might actually intend. So you'll get R attached on there or there. Whoops, this was meant to be a bromine. Yeah. I think that's all of the difference. Cuprates can also act somewhat as SN2 reagents. Like you can just use them to do SN2 kind of. But that also in part just goes by like this. Like sometimes it's coupling instead of SN2 or something. It's kind of complicated. For our sake here though, because we're just reacting with an acid chloride and not doing all of this complicated stuff, it's nice because it just makes a ketone at the end.
Got it. Thank you. That was
Yeah.
a helpful review.
Yeah, I know. This is always involved, and it's like always really hard to remember what all of these.
I'm still a little confused on how to use organocooperates. Can we do an example of using them?
Well, yeah, let's just do it here. So,
Perfect.
yeah, in this case, right, we have this cuprate and an acid chloride, and the cuprate is strong enough to add once. Like this. And if we were using like a Grignard reagent or an organolithium, then it would add a second time because it's a ketone, right? It's perfectly good to react with. But cuprates are too weak to react a second time. So it'll react once to get the ketone, but then it says, well, you know, I'm too weak to react with the ketone, so I'm just stuck here, right? So this ketone just stays as is at the end. So it'll only react once, which is, I guess, pretty desirable in this case, because if we go way back at this point, up to here, this is the product that we want, right? And we have this methyl on here, so now we just have to think about how to add an amine.
I'm sorry, I lost track for 1 second. Which molecule have we formed at this point? There, okay.
Yeah.
So, are there ways to go from an alcohol to an amine?
No.
Okay.
There is a way to go
Could you make
Yeah.
like that.
an imine and then reduce that double bond?
Yes. Yes. What is that reaction commonly known as?
The Wolff-Kishner? No.
Wolff-Kishner gets rid of ketones altogether.
Right.
Right. So we're making an imine and we're reducing it, and it requires special reducing agents. So you actually don't need to know the name of it. If you don't, it's fine. It doesn't. Knowing the name of it doesn't help you remember how to do the reaction. So this is a reductive amination.
Right.
That we're doing. Yeah, this is one of our strategies for making amines. In fact, it's like probably one of the most common or like most useful of these strategies. So to make the imine, all that we have to do is, well, we add H2N methyl, right? Imine formation only happens under acidic conditions, right? And then we have to reduce it. Let me rewrite this because it's ugly. Then we have to reduce it. So do you guys remember what reducing agents we use here? I think there's 2 of them, but either one.
The specific ones with sodium, right? So you can do like NaBH2CN. I guess that's sodium borocyanate or something. And
Yeah.
then NaBH.
Did you do the Na2 CR07?
That'll oxidize, not reduce.
Oh, okay. Yeah.
Yeah.
Sorry.
Yeah, is it NaBH3CN? Is there 3 CNs and 1 hydrogen? I can't remember.
I have written down NaBH2CN. I could have written it down wrong.
Oh, no, that. No, I think the boron should have
3.
four substituents.
Okay.
Well, it's one of the 2. This is certainly we have the right idea, so it doesn't.
Okay.
Yeah, it's something that I guess is worth looking up and checking what the exact thing was. I think the other one is sodium.
I have NaBH and then 3 OAC.
Yeah.
That is.
Yeah.
So- Sorry, go ahead.
In this case, it's probably 3 cyano groups, I'd bet. But I can't remember exactly. Yeah, and so you do this one step after another, and you wind up getting an imine. Where you wind up getting an imine, and then from there you reduce it. I had said earlier. Go ahead.
No, I'm sorry. You go ahead. I didn't mean to cut you off.
I had said earlier actually that like you can do this entire synthesis in 2 steps. And this is where that's the case, because you actually don't have to do these in 2 separate steps. You can put all of it in the same reaction, and it'll first make the imine and then it'll reduce right away, which is why reductive amination is pretty nice as an option.
So could you use a reducing agent to make your ketone into an alcohol, and then replace that with a good leaving group, and then add your amine that way?
Okay, yeah, I guess that's an option. Yeah. It gets a little bit dicey because you'll have a secondary leaving group. So let's do like tosyl chloride, right? Then we need pyrimidine too. So this is an option. We do NH2 methyl, the same thing we've been using for a while. Right, and then again, use some base to do this. This is, since it's a secondary leaving group, it's a little bit like iffy, but this should work too. Actually, you don't need pyrimidine in here because this itself is a base. So excess of this will work, but that's whatever. Yeah. Okay. Yeah, this is definitely the shortest way to do it. You can take a few steps to get here, right? Like that's totally possible, or like you can do that. But I mean that one you guys can figure out, right? Whatever way of getting from this start to this end that works would be fine. I think that reductive amination is the only way to get this final product though. Like I think whatever way you want to do the synthesis, you will have to do reductive amination at the end. Okay, maybe not necessarily, but any other way would probably get really involved. Let's pick a new one. Oh, we're all the way at the bottom. Okay. Let's make a new page. And get a new problem on there. Okay, cool. So here we're we're starting off here, and then we're, I guess, adding this this carbonyl and making an amide out of it. Okay. Seems reasonable.
That's going to be a pair director right away. So you can just
Easy.
use steel crafts to make a carbonyl.
So we should just Friedel crafts. Yeah.
Or Gatterman
In this
Koch.
case, we might want to Gatterman Koch here because COH2 CH2O, whatever. Yeah, this seems reasonable. So we can put an aldehyde on there. Okay. And from there,
make an amide out of an aldehyde.
somehow we're gonna have to get rid of this hydrogen altogether. So there's no like pretty way to do it. Like it takes a few steps to just get rid of this and convert it. So I don't know. However you guys think that's a good idea. However you guys think we can do that.
I mean, if we want to use NH3, we first need to have the acid chloride, right?
Yeah. So yeah, at the end of the day, we could.
I feel like maybe instead of putting the aldehyde on there, couldn't we just put like, make it a carboxylic acid and then go from the acid to the acid chloride?
Yeah, that's smarter. I I like that better with SOCl2, right?
Yeah, yeah.
Then we're good.
Sure. Yeah, so we could do that too. Just to finish this one off, because this is a totally fair synthesis pathway. Yeah, we could just oxidize here, right? Like, I don't know, use whatever you like, bleach, right? SOCl2 and finish, right? But you're right, we could also, yeah, we could make a Grignard and then put the acid on there with CO2. So we could also do like PR2 with FeBr3, or aluminum trichloride if you're feeling, you know, not remembering, right? And then so then we'd have a bromine, right? And actually we'd wind up just going right back up here to this part of the pathway once we add magnesium, then we add CO2, and then we do an aqueous workup. Okay. At the end of the day, it's actually the same number of steps.
Yeah.
So yeah, I don't think there's a much faster way of doing this. You know, I guess in theory you could go this way by adding NH3 and then heating the hell out of it. That's not a very good reaction though, so I wouldn't place my bets on it. Sorry, I meant from this acid. Yeah.
The most intuitive to me is probably to make your reactive acid chloride and then just use NH3.
Yeah. This is definitely the more the higher yield way, right? Like, because once you have this acid chloride, making the amide is like instant. It's really easy. So
I think
you,
in this chapter, like the narrative, I guess, is making more reactive groups in order to produce less reactive ones, kind of go down the hierarchy a little bit.
yeah, that's a common thing, right? Because when you have that hierarchy, it's always easy to just drop all the way to the bottom to acid, but from there it's easy to go back up to the top, and from there you can go wherever you want. So it's pretty common to just do that. Yeah, it's pretty easy. I guess in practice that's probably not desirable, because I don't know, maybe like SOCl2 is like toxic or poisonous or explosive or something, right? I'm sure. But we don't worry about that.
How do you make an acid out of a ketone again? It's just slipping my mind.
You can't.
Can you easily do
make
that
an
or
acid,
no?
right? Because there's no like acidic hydrogen to lose.
Can you like? Oh, all right. Never mind. I was gonna
Oxidize it.
Yeah, you can't remove an alkyl, and you can't remove like any of those
Right.
carbons.
Right.
Yeah. Yeah. Losing a carbon from there would be a bit more involved.
I was just looking at this, and we couldn't do this with Friedel-Crafts as opposed to Gatterman, Koch, Koch. Yeah. All right. Cool.
No. All right. One more synthesis. Go. And, oh wait, is it? Oh, it's there. Okay, cool. Let's see. All right. So we have our ketone, and now we're adding a bunch of other stuff into it. Yeah, great.
Fun.
Yeah, I know. Well, okay. Well, I haven't looked at this one before, so I have no idea. So what do you guys think?
Could we use like an organolithium?
To
add
attach
to
what?
the carbonyl.
So what do you want to attach?
Let me go for the phenyl.
Sure. We can add phenylithium, right? Let's do an aqueous workup afterwards. Just for have that, right? And then let's do this phenyl.
And then can we, so we have our alcohol now. Can we use that as like a leaving group to add on a bromine? I'm not thinking too far ahead, but maybe make a Grignard.
I see what you're saying.
Is there a way to just like oxidize that alcohol to an acid, and then we could just make an ester after that?
Not from here. You can't oxidize the alcohol at all because there's already three carbon bonds on here. Yeah. Okay, so Paul, what you were saying makes sense. Let's make the alcohol a good leaving group first.
Okay.
Before we try to go for SN1, because it's a tertiary carbon, so that's all that we have. We can only do SN1. So let's do OTS, right? And then add sodium bromide.
And then we can make our Grignard, and then we can do CO2, and then we can esterify.
Yeah,
like
right.
Fischer.
And then from here, yeah, you know what to do. Yeah, that probably works. The part that sucks is doing this, because I mean, of course it does. It's an SN1, but I don't know. It seems like it works. Yeah. Are there other ways to do it? So I was thinking, no, this seems like it. I can't think of any other way to do it.
This makes sense to me.
Yeah. I think this is it. Yeah. Oh, I checked the solution. This is the same thing that it was written down there.
Just to finish it off, we add Mg, we do CO2 and H3O plus, right? And then after that, we esterify. It's just methanol, right?
Yeah.
Methanol and also acid workup.
So, there's actually not that that's perfectly fine too. You can also use a different way to make the ester that is much more reliable. You know what I'm thinking of? Because if we're just using the Fischer esterification, then we have equilibrium.
Is it the diazomethane? Yeah.
Yes. Yeah. So you can also use diazomethane.
Yes, and you just form an OH. Okay.
Yeah. And diazomethane reacts amazingly to make methyl esters. So.
All right, it was just like a revelatory moment because I remember he talked about how it's super high yield. So I was like, all right, that's
yeah, exactly.
Cool.
So it's an option. Yeah, there's one more question on the worksheet, which looks like this. So we'll look through it quickly. Okay.
Oh man.
Yeah. So this here is actually a sugar, which is what you talk about in chapter 23, which you're not at yet. So, however, you don't need that to do this problem. You don't have to have seen sugars to do this problem before. So the only thing that you need to know to do this problem, which I'll point out to you, is that if you look at this carbon, this is an acetal, right? Because it's connected to 2 oxygens.
Okay.
So, well, what happens?
It's acetals are they're unstable and they're just going to form the carboxylic acid. It's going to break there.
So I don't think it's going to form a carboxylic acid, but it's definitely going to break here. So let's just go with that. Okay.
Oh, it's going to form the diol.
Yeah.
No, the
well, or it'll form the ketone or the aldehyde.
Okay.
Right. Yeah. But well, we don't need to worry about that. Let's just go with it.
Okay.
So here's the terrible thing about sugars is that they're just a massive pain to draw. There we go. So here's an oxygen, right? Here's that carbon we're working with. Okay. So we've protonated now, so OH plus. Okay. Oops. Yeah. Okay, so we've protonated now. And now how do we break the acetal? Remember, when we have acetals, normally what we would do is, if we had something like this, right, we would protonate here. And then this would kick this off. So let's just do the same thing. So we wind up with our sugar. Which has this weird double bond within it, but that's okay. We're not as worried about the sugar, right? You'll learn how to deal with that in 2 chapters, but we're not so worried about that. What we are worried about is this other thing, which the problem said is makes some toxic compound. So that's what we're worried about. Okay. So this is what we have, and then are we done?
I know that the the nitrile will react with the acid. But I
Yeah,
like what happens.
Yeah, it will, exactly. And then, so at the end of the day, we form this.
All right.
Okay. This is not a toxic compound, however. But what we release is
the gas, nitrogen gas, N2, right?
N2 isn't harmful.
Well, that's true.
Yeah. But
Are you asking what the byproduct is?
yeah, actually, I don't think this is the product you get at the end of the day. I think you get something else. But yeah, at the end of the day, the question is, what is the byproduct here? Oh, so maybe instead of taking this off, you might also notice that this carbon here has an alcohol and a cyanide group on there at the same time, which is like a cyanohydrin, I think, right?
Yeah, sounds right.
And so this alcohol is actually going to want to pop this thing off. Okay. And so we'll have this methyl and then this, right? And then plus a CN minus, right?
HCN.
And you would deprotonate it, right? Yeah. Yeah. Okay, this is toxic, right? But that one, right, you know.
To be honest, I'm glad to wait until chapter 23 for these sugars. It's okay.
Yeah, that's pretty reasonable. Yeah, sugars suck. It's just it's like the worst chapter. And proteins, not a fun chapter either. Even if you're interested in either of those 2 things, it's just not good chapters. All right, cool. That covers all of them.
All right, awesome.
So-
Thanks so much as usual. It's been very helpful.
Yeah, cool. So good luck on the quiz like next week or whatever. There's no quiz next week, the following week, I think. But I think we'll probably still have a workshop anyway, because
Okay.
chapter 22 was pretty involved.
Okay, so there's no, I'm sure it's in the syllabus, but yeah, it makes sense. There's a quiz next week, but nothing next Saturday, because we're not going to cover material this Tuesday.
Yeah.
Okay.
Yeah.
Cool.
All right.
Yep.
Sounds good.